This is a short video on a couple of things I didn't cover on the previous pH and indicators videos, and they're things that you need to be aware of. So the first thing is when we're using this expression to work out the concentration of H ions for weak acids, is that we're making a couple of assumptions in order for this to be valid. So the first assumption is that when the acid ionizes as it dissolves in water, the concentration of the acid remains constant, which obviously isn't true because some of these will disappear in forming the ions. So that's one big assumption, that the concentration of the acid doesn't change when you dissolve it into water. This assumption is fine for very weak acids. However, if you've got a weak acid that ionizes quite significantly, this will make the expression here not valid. So this is really an approximation, and often we change the equal sign to that. The second assumption is that the H plus ions in solution that causes the pH of the solution is only coming from the acid itself. Well, that's not true, because there'll be some H plus ions from water dissociating, ionizing, because water, we know, ionizes not significantly, but it does ionize. And this will be an issue if we've got a very, very dilute solution of the weak acid, because that means the number of protons from the water ionizing is more significant. So there's another assumption we have to be aware of when using this equation. So the other thing that I didn't cover when we did indicators was how to choose an indicator using the pKa values of indicators. So as we said, an indicator is basically a weak acid with the undissociated indicator as one colour and the conjugate base of the indicator being another colour, and the colour you see will be the combination of these two colours. So we can write this equilibrium as if it were an acid equilibrium, and here's my two colours of the indicator. So this could be the red and yellow for me for orange. And we can write the Ka expression for this indicator, the acid dissociation constant for the indicator. So don't forget, this is not an acid we're looking at, this is the indicator we're looking at, which is a weak acid. So we can group these two parts of the expression together to give this, and separate this out. Now the end point of the indicator is where the concentration of the undissociated indicator equal to the concentration of the conjugate base of the indicator. So when these two are equal, these two values will cancel each other out. So effectively, this then becomes this. So we already know that these values can be quite small, and it's easier to list them in tables and so on by taking minus log of these values to get pKa values and pH values. So the end point of the indicator, or the pH at which we get the intermediate colours of these two, is the same as the pKa value for the indicator, and these values we can look up in tables. This is useful to know if we know roughly where the equivalence point is for a titration, so we can choose an indicator by looking at the pKa values of indicators which are listed in tables. So we want the pKa value for the indicator to be close to the equivalence point of the titration, as this will mean the end point of the indicator will fit into the vertical section of the pH curve for the titration.